Howdy folks. In this video I want to talk about the parameterizations of level curves and contour curves. And if you read through this statement, what we give is a differential equation along with initial condition, where if you solve this differential equation, you'll be able to both parameterize contour lines and, parameterize both level curves and parameterize contour lines based on the solution G to that differential equation. So let me show you how this works. Suppose we have this surface, where this surface is some surface f of xy. And let's take one of these contour lines, maybe this line right here, which would be the contour line where f of xy is equal to c. So our strategy, we want to come up with the equation or a parameterization of this contour line. That is, we want to come up with some sort of r, and I'm using the subscript c there for contour line. We want to come up with some sort of parameterization of that curve. So our strategy is to first project that curve down into the xy plane, the domain space. And in the xy plane or the domain space, that would look something like this. And so this would be the level curve for f of xy equals c. And so this is we call this a level curve, whereas we call this a contour curve. So what we're first going to come up with is we're going to come up with the parameterization of this level curve, and then it's just an easy step to take this level curve and then bump it back up onto our function. So the question now becomes, how do we find a parameterization, and before that, how do we find an equation for this level curve? So finding this equation is going to hinge on a couple of observations. The first one is that oftentimes, and this is why I'm kind of careful with my language here, oftentimes we can use this, what I call the standard parameterization for a curve. That is, we could go ahead and parameterize a curve by saying, let's let x of t just be the variable t, and then we will solve f of, normally this would be x comma y equals c, but we're going to replace that with the x of t, which is just t there. And if we can solve this for y, we could call y sub t that solution. Okay. Now, we don't know how to find that y sub t. That's what our differential equation is going to help us do directly. But if we had that y sub t, then we could use as a parameterization r sub l of t would be equal to t comma y sub t. Now, sort of a trick of notation here is if I'm letting x of t be t, then there's really nothing different than calling x t. They're synonymous with one another. So another way I could have just done all this is I could have said, let's let x equal x, and then we're going to solve f sub xy for c, for y, and call y sub x that solution. So there's nothing new, we don't get anything by introducing t into this, so let's just go ahead and keep everything in terms of y and x. So that means we would describe the parameterization of that level curve line as a function of just that first variable x, and we would write it as x comma y sub x. Okay. Now that we've got that, we're going to make use of a clever trick that we developed in one of the earlier videos, and that is, we know that the gradient vector to this function f, the gradient vector of this function f, is always orthogonal to the tangent lines of this level curve. That is, if we were to go put a tangent line onto this level curve right here, that tangent line would always be orthogonal to that gradient line. So there's the gradient vector. I said gradient line, folks. I should have said gradient vector. There's the gradient vector. And let's dot it with a tangent vector to this level curve, which, if we're using this particular parameterization, a tangent vector would be r prime of x. And these two we know to always be orthogonal, so that dot product is always going to be 0. So if we take the gradient as a function, that would be f sub x comma f sub y, and we're going to dot that with r prime of x. Well, if we differentiate this with respect to x, the first coordinate would be just 1, and the second coordinate would be, I'll go ahead and write it this way, as dy dx. Now, to develop the differential equation that has to be solved in order for us to find out what that y sub x has to be, this differential equation that we're trying to prove why that's what we want to solve, we can just solve for dy dx by doing this dot product. So if we compute this dot product, we'd have f sub x, and if you like, you could put times 1, plus f sub y times dy dx needs to equal 0. And solving that, we get f sub y times dy dx has to equal minus f sub x, or we get that dy dx has to equal minus f sub x all over f sub y. You can see here why in the opening statement I said that this only would work if f sub y is non-zero. So solving this differential equation, this is the differential equation that we wanted to show. Solving that differential equation together with an initial condition will give us some result that we could call either y sub x or g sub x, as I did here. So let's add to this that we have the initial condition together with, so let's say it like this. Let's solve the differential equation dy dx is equal to minus f sub x over f sub y with y sub a equal to b. If we solve this differential equation right here, let's call the solution remember, when you solve a differential equation, you're finding a function, so call that solution g sub x. Okay. Real quick, I guess I should say this. For that initial condition, what we need is we want this level curve right here, which passes through the ordered triplet a, b, f of a, b. Or if we're just looking in the domain, this would be the ordered pair a comma b. That's the domain value that gives us that ordered triplet on the graph. And so that's the initial condition we want. Folks, if you don't remember differential equations from your Calc 2, the reason why we need an initial condition is because this could create, the solution to this standalone differential equation gives us an entire family of functions, all that have sort of the same shape of level curve, maybe living in the domain space, but we specifically want the one that passes through the ordered pair a comma b. And so we need to specify that initial condition right there. So that's why we need the initial condition. So those two, when you solve this, and by the way, folks, if you're feeling like this is very abstract, we're going to work an example of this. But let's call the solution to this differential equation the function g sub x. So once we've got that, we're basically done with the problem, because that tells us that we can write our r sub l of, if we wanted to write it in terms of x, it would just be x comma g sub x, because g sub x gives us that function that we wanted. But normally when we give our parameterizations, we use the variable t here, so I'm going to do that. I'm just going to switch the variable t here, and this parameterization right here would describe this level curve, and we obtain the function g by solving this differential equation. Then, if we want to project this back up onto our surface, we simply need to add in that third coordinate, and so we would have the parameterization t comma g of t, and then we would go ahead and take those two, this x coordinate, this y coordinate, and let's plug them into the function that is the surface. So it'd be f of t comma g of t, and then that gives us the appropriate, takes this point in the xy domain plane and then bumps it up to that particular z value up here. Now, of course, this should always be outputting the same, when you do this, it will always be outputting the same value c, but that's how we would give that parameterization to that curve. Folks, if you have any questions on this first part, let me know, and in the next part we're going to look at that other formalization for finding the curve of steepest descent. If you have any questions on this, let me know. So now that we've described how to find the parameterization of a contour line, we now want to focus on the parameterizations of the curves of steepest ascent and descent. So again, we've got this function that's differentiable at some initial point, and because we've got division in the differential equations we're going to derive, we need the respective partials not to be zero for whichever one it is. So read through this, folks. This is our statement. This is the roadmap for how to build the curve of steepest ascent or descent. And what I'd want to do is justify why it is we need to solve this differential equation here. The rest of this, constructing the curve, the parameterization of the curve of steepest ascent and descent in the plane, or those two curves in 3 space, that's not a big deal. It's very similar to what we did in the last video. So let's take a look at this here. So this is the same image we had before, but now we're going to talk about moving along the path of steepest ascent. So as a reminder, to do the path of steepest descent, what we need to do is we always need to move perpendicular to well, let's do it from here. We want to move along a path that is always perpendicular to the various level curve lines. So maybe that's that level curve line, and then maybe we have this level curve line. So we always want to do the path of steepest descent, we want to be moving always perpendicular to those level curve lines, which means we want to be following the direction of the gradient. So it's like we compute the gradient at a point, we step in that direction. At that new point, we compute the gradient, we step in that direction. So how are we going to do that? Well, I'm claiming that all we need to do is to solve this differential equation right here. Let's look at why that's so. So in the previous part of this video, we showed that if we wanted to move along the path of no change, that we would find g sub x. So we would solve to move along the contour line, or the level curve, I guess I should say, to move along the level curve, meaning this blue level curve down here, what we did was we solved, let me scoot over here, we solved the differential equation dy dx was equal to minus f sub x over f sub y with the initial condition y sub a is equal to b. Well, this gave us the curve of no change, meaning that our z coordinates didn't change as long as we continued along this curve. We want to be moving perpendicular to it. So now, and by the way, we called the solution was g of x. Now we want a function that is always perpendicular to this function g sub x, meaning we're moving along the direction of the gradient. And how do we find the slope of a perpendicular line? So remember, a differential equation really says we want to come up with a function where the slope is always this. Well, now we want to come up with a function where the slope is always perpendicular to what we had. So now we want to solve the differential equation dy dx is equal to, and how do we compute a slope perpendicular to this one? Well, two lines are perpendicular if their slopes, remember, are negative reciprocals of one another. That's something we saw in Calc 1, in algebra. So if I take the negative reciprocal of this, I would just have f sub y, in fact, let's do it like this. We'd have negative f sub y over f minus f sub x. And so we end up with just needing to solve the differential equation dy dx is equal to f sub y over f sub x. And that's the differential equation that we need to solve to find the path of steepest ascent or descent. You can worry about maybe adjusting the minus signs on here to worry about whether it's ascent or descent, but in my opinion, it's easier to just compute this curve here and then make sure that when you give the parameterization, you're heading in the direction you want to go for ascent or heading in the direction you want to go for descent based on just checking the gradient vector at one point. So folks, that's about all I have to say about this, because once you have that, once you solve this differential equation, and I guess we should add that it has the differential with the initial condition, again, that y sub a needs to equal b, let's call the solution h of x, then the parameterization of the path of steepest ascent, or a parameterization for it, would just be, so I use a for ascent there, the parameterization of the curve of steepest ascent would just be t comma h of t that gives you this curve right here. And if we want to then give us this curve up here, we get the x-coordinate and the y-coordinate from our domain, and then we get the z-coordinate by just simply plugging this in for x into our function f, and this into y into our function for y. So this would be f of t comma h of t, and this gives us the path of steepest descent. Folks, one thing I'm being very careless about as we're doing this problem is the issue of doing the domains. So notice I say special care should be taken to compute the domains of these parameterizations. Because this is really just meant to be an overview of where these differential equations come from, I'm not really going to discuss the domains of the parameterizations. But the long and short of it is, you want to make sure if you're computing the path of steepest ascent that you do indeed head in the direction of the gradient. And so when you choose your domain, make sure that that's what the parameterization is laying out. And if you want the path of steepest descent, which maybe would be continuing on this way, then you would want to adjust the parameterization so you're moving in that direction as time progresses forward. I hope this is helpful, folks. It's not essential that we fully grasp where these differential equations come from, but we will work an example of it later on in this handout. Thank you very much.